Welcome to solverfy.
Question number 57 is a weak base, strong acid titration problem where you are given 8 different volumes during the titration process and asked to calculate the pH at each of those 8 volumes. To do this, we need to recognize that when we start with a weak base in solution, pH is determined using a Kb weak base calculation. Then once the titration begins and strong acid has been added, some of the strong acid will convert the weak base into weak acid and we will have a buffer solution. So pre-equivalence, all pH calculations will be buffer solution calculations using the Henderson-Hasselbalch equation. At the equivalence point, all of the weak base will have become weak acid, and we will perform a Ka or weak acid pH calculation. Then post-equivalence, we will have excess strong acid, and we will determine the pH simply based upon the excess strong acid concentration or the excess hydronium concentration. So let's get started. The first volume of strong acid added is 0 milliliters. If we have added 0 milliliters of strong acid, then all we have in solution is the weak base. To carry out the pH of a weak base solution, we simply need to first solve for the hydroxide concentration. The hydroxide concentration, as you recall, for a weak base is simply equal to the square root of Kb, 5.2 times 10 to the negative 4, multiplied by the concentration of the weak base, 0.1 molar. This is our hydroxide concentration. If we divide this into Kw, we will get the hydronium concentration. If we take the negative log of the hydronium concentration, we will get our pH of 11.86. Next, we have added 10 milliliters of the strong acid to our weak base. Because we started with 20 milliliters at 0.1 molar of the weak base, and we are adding 0.1 molar HCl, then we have a 20 milliliter equivalence point. So if we are at 10 milliliters, we are halfway to the equivalence point, and as you recall, the pH at the equivalence point equals pKa. pKa is simply Kb divided into Kw. This will give us our Ka value. We take the negative log of that, we'll get our pKa, and we'll recognize that at half equivalence, pH equals pKa. If you didn't recognize this, you could still use the Henderson-Hasselbalch equation and you will get the same answer. pH will be equal to pKa plus the log of the moles of base. The moles of base will be equal to the moles of base we start with, which is 20 milliliters or 0.02 liters at 0.1 molar, minus the moles of strong acid added, which will be the 10 milliliters or 0.01 liters multiplied by its molarity of 0.1. This will be the moles of strong base left in solution after 10 milliliters, weak base left in solution after 10 milliliters of strong acid has been added. We divide that by the moles of weak acid formed. The moles of weak acid formed will be equal to the moles of strong acid added, which is our 10 milliliters, 0.01 liters at 0.1 molar. This also gives us our pH equal to pKa at 10.72. The next calculation, C, is similar to the previous. We still have a buffer solution. We are still pre-equivalence at 15 milliliters, where equivalence is 20 milliliters. So we still use the Henderson-Hasselbalch equation. pH is equal to pKa plus the log of moles of base, which will be the moles of weak base we start with, again 20 milliliters at 0.1 molar, minus the moles of strong acid added, which can be calculated by taking the volume of strong acid added, 15 milliliters, or 0.015 liters, multiplied by the molarity. We then divide that by the moles of weak acid formed, which will be equal to the moles of strong acid added, the same calculation as we did up here. This then gives us a pH of 10.24. Because we are adding strong acid, we should see a decrease in pH throughout these titration calculations, which we are currently seeing. Next, for part D, we've added 19 milliliters. We are still pre-equivalents, so we are going to still use the Henderson-Hasselbalch equation because we still have a buffer solution. But this time, instead of the 15 milliliters added, we've added 19 milliliters, or 0.019 liters at 0.1 molar. So we'll also change that down here in the denominator when we calculate the moles of weak acid formed. Other than that, the calculation is the same, and we get 9.44 as our pH, still decreasing as we are expecting it to. For part E, we are at 19.95 milliliters, so still pre-equivalents, still a buffer solution, still using the Henderson-Hasselbalch equation. This time, however, we're using our 19.95 milliliters instead of the 19 or the 15. 19.95 milliliters is 0.01995 liters. This will be the decrease in the moles of weak base and the increase in the moles of weak acid. And we get a pH of 8.12. Now we are at 20 milliliters. At 20 milliliters, all of the weak base has been converted into weak acid. If all of the moles of weak base have now become moles weak acid, then we have a weak acid, or Ka, calculation. To calculate pH, we need to know the hydronium concentration that is being produced from the weak acid. The hydronium concentration will be equal to the square root of the Ka value, which we don't have, but we do have the Kb value. We can calculate the Ka value by dividing the Kb value into Kw. So Kb divided into Kw gives us Ka. So the hydronium concentration is the square root of Ka multiplied by the concentration of our weak acid. We started with 0.1 molar weak base. All the weak base has become weak acid, but we doubled the volume. So the concentration of the weak acid is half the concentration of the weak base we started with because we doubled the volume. This will give us our hydronium concentration once we take the square root. Then if we take the negative log of this hydronium concentration, we will get our pH at 6.01, still decreasing. Then going to part G, we are post-equivalents. If we are post-equivalents, we have excess strong acid, because the strong acid is our titrant. To calculate the pH, we simply need to figure out the excess strong acid concentration, which we can determine by first calculating the excess strong acid moles. These are the total moles of strong acid we have added at 20.05 milliliters, or 0.02005 liters, 0.1 molar. We'll subtract off the moles of the strong acid that reacted, which will be equal to the moles of weak base we started with at 20 milliliters, 0.1 molar. And then we divide by our new volume. 20 milliliters plus the 20.05 milliliters is 40.05 milliliters, or 0.04005 liters. This then gives us our excess hydronium concentration. We take the negative log of that to get our pH at 3.90. For the last one, it's the same calculation as we just did, but now we will be using 25 milliliters, 0.025 liters, instead of 20.05 milliliters, or 0.02005 liters. And the new volume, of course, is going to be the 20 plus the 25, or the 0.05 total. And we get a pH of 1.95.